Hello students, welcome to the 37th lecture on particle physics. And today we are going to talk about neutrino oscillation. In fact, in the next 2 3 classes, we shall discuss about the neutrino oscillation parameters, the different experiments which are looking at these oscillation signals and determining the parameters, what is the current status, etc. And what I had told you that neutrinos come in three flavors in the standard model of particle physics: electron type neutrino, muon type neutrino, and tauon type neutrino. And we saw that electron type neutrinos are produced in the core of stars. In the reactors, we have the production of anti-electron type neutrinos all the time. Then during the supernova explosion, we have all the six flavors of neutrinos. If we talk about accelerator neutrinos, then pions and kaons, they decay to muon type neutrinos or muon type antineutrinos depending upon the magnetic field. But if we allow them to travel to a longer distance, then this nu mu may change into nu e or nu tau. And it has been observed that even in the accelerator experiments, that here also neutrino oscillation has been seen. It has been confirmed by solar neutrino experiments and atmospheric neutrino experiments that we talked about in the last class. And what we are really talking about is that neutrinos are changing from one flavor to another flavor. The similar picture that has been shown in this slide is true for antineutrinos also. Therefore, what is neutrino oscillation? An initially pure beam of a particular flavor of neutrino, say I am talking about nu mu, will turn into another flavor of neutrino, say nu tau, while propagating, which will turn back into original particle, and so on. And therefore, this is what we call it as neutrino oscillation. That means if we are producing 1 million of muon type neutrinos, and we have placed a detector at some distance, and through this interaction, say nu tau n going to tau minus plus p, this is tau minus plus p. If we are observing tauons in the interaction, then that means while nu mu's were coming, on way a few of them have got converted into nu tau, and because of this interaction, you have a charged lepton tau of tauon type in the final state. Or if we have placed a detector which is sensitive to for detecting electrons, then we will say that we are observing electrons in the oscillation of nu mu into nu e. Now this is about neutrino oscillation, the basic pictures, changing flavor from one to another. If you recall, then even while we were discussing about snow experiment, where we talk of detecting neutrinos from sun in the neutral current interactions, we saw that a standard model prediction for the solar neutrinos coming to Sudbury Neutrino Observatory that agree with the experimental observation. While if we talk about only nu e, then nu e was found to be much less in number, and that is why we say that some of them have got converted into nu mu and the others into nu tau, but the net is that we are getting the same number as was predicted in the standard solar model. Now, this neutrino oscillation is purely a quantum mechanical phenomena, and in the quantum world, particle and wave are different aspects of the same physical state. As we have discussed wave particle duality, we have talked about electrons as a particle as well as a wave. We have seen that experimentally we see electron diffraction pattern, we see neutron diffraction pattern, as well as we treat neutron to be a particle. We have neutron scattering experiments and all that. Then photon is a wave, as well as the Compton scattering tells us that photon behaves like a particle also. Therefore, in general, all the fellows that we talk about, including humans, they have both the behavior particle like as well as wave like. In the microscopic system, we talk about for electrons, protons, photons, neutrons, etc. It's easy to see the diffraction pattern or interference pattern or the particle behavior. But for macroscopic systems, we only talk about the particle nature. But in fact, it is this wave nature is there everywhere. Now, a particle with a certain energy is described by a corresponding wave of a certain frequency. In quantum physics, the electron, muon, and tauon neutrinos are represented by superposed waves that corresponds to neutrino states with different masses. Therefore, what we say that actually nu e, nu mu, nu tau, or nu e bar, nu mu bar, nu tau bar, they are production states as well as they are detected in the experiments. But when they propagate as the combination of mass eigenstates. Therefore, what I am telling you that I have got a proton beam, it strikes a target material, it produces pions and kaons, and these pions, kaons in a magnetic field, when they travel, they get collimated and they produce neutrinos. I am not talking about which neutrino. They produce muon type neutrinos or muon type antineutrinos. And then this nu mu travels in space, and if we are observing some interaction like nu mu interacting with a neutron target, giving us muon and proton in the final state, we say that okay, we have observed muon type neutrinos. Now, if we had started with 1000, say for example, muon type neutrinos, and here we are seeing numbers which are smaller than this, then we will say that we are talking about disappearance experiment. How many muon type neutrinos have got disappeared, or how many anti-muon type neutrinos have got disappeared. But if our detector is sensitive to detect electrons, then or tauon, then we will say that these are the appearance experiment. That starting with a nu mu beam, you are looking for the electron signal. That means you are looking for how many of nu e we are observing, how many of nu tau we are observing. Therefore, this is an appearance experiment. Therefore, two types of accelerator experiments are being performed. One is the disappearance experiment. You see how many nu mu or nu mu bar have got disappeared, or appearance experiment, how many nu e bar or nu tau bar you are finding out. Therefore, what we are saying that when a nu mu is traveling, it does not travel at as nu mu, but it travels as a combination of, say, in the two flavor neutrino oscillation, of mass agonist states nu 1 and nu 2. Therefore, what we say that we have in the two flavor oscillation scenario, we have nu mu and nu e as the flavor states, while they travel as mass agonist states nu 1 and nu 2. And what is nu mu? This is cos theta nu 1 plus sin theta nu 2. This is a unitary matrix, and in absence of mixing, theta will be 0, and that means nu mu will be nu 1 and nu e will be nu 2. But when mixing is there, which we are considering, this theta will be non-zero. Therefore, this is a unitary matrix, and we are talking about propagation states as nu 1, nu 2 and nu 3 for three flavor neutrino oscillation. And for two flavors, just we will talk about it, where we will take simple case and then we will generalize it to three flavor scenario in the next class. But here what we are talking about, that we have two flavors, we have theta as the mixing angle. Therefore, when the waves are in phase, it is not possible to distinguish the different neutrino states from each other. But when neutrinos travel through space, the waves go out of phase. Along the way, the waves are superposed in varying ways. That means this nu 1 and nu 2, they have got different masses. Say one is m1 and another is m2. Because of that, they have got different frequencies, and when they travel in space, they are traveling as in the different phases that gets developed as they travel in space. And this superposition of these two waves, somewhere it will give rise to nu mu, somewhere it will give rise to nu e, and all that. Therefore, this oscillation from nu mu to nu e and then back to nu mu will happen as the neutrinos will travel in space. Therefore, what is happening, that we have flavor states as the production state or as the detection state, as we have seen that we are detecting electron or muon or tauon in the final state, because nobody can see directly a neutrino, that we have discussed. Therefore, we are talking about the signature of nu e, and signature of nu e will be an electron in the final state to conserve lepton quantum number. Signature of nu mu will be a muon in the final state. Therefore, what we are talking about, that we have nu e and nu mu and nu tau as flavor eigenstates, and they are the production states obtained either through, say, pion decay or kaon decay, or inside the core of the sun, or at the reactors, or during supernova explosion. But when they propagate in space, the neutrinos which are coming from the sun, when they propagate in space, they don't propagate as flavor states as nu mu or nu tau or nu e. Rather, they propagate as nu 1, nu 2, nu 3 states, which are superposition of this nu mu or nu e or nu tau. And these different states, they have different masses, they have different frequencies, and since they have different masses, therefore you can say that the energy of these particles are different. E1 is square root p square plus momentum is the same, and they are the momentum states, but the energy is different because the difference in the masses, and this results in the difference in phases as it propagates in space. And because of that, when there is an overlap of these two waves, you have nu mu, or at other length you have pure nu e, and similarly as you move out. Therefore, the superposition in any given location yields the probability for what type of neutrino is most likely to be found there. The probabilities vary from one location to another. They oscillate and the neutrinos appear in their various identities. This peculiar behavior is thus due to the difference in neutrino masses. Now, in the context of three flavor neutrino mixing, we have three mixing angles, which generally is called theta 1 2, theta 1 3, and theta 2 3, because there we are talking about three flavors of neutrinos, and one additional phase that we call as CP violating delta phase. This we have discussed at length while talking about matter antimatter symmetry. These parameters collectively describe the transformation of neutrino flavor eigenstates into mass eigenstates as neutrinos propagate through space. Now, the mixing angle determines the probabilities of neutrino transition between different flavor states, while the CP violating phase introduces a complex phase factor that can lead to differences in oscillation probabilities between neutrinos and antineutrinos, contributing to the phenomena of CP violation. Remember, when we were talking about CP violation, what I had told you, that the probability of nu mu to nu e, if it turns out to be not equal to probability of oscillation of nu mu bar to nu e bar, then we will say that CP violation is taking place. Now, these three mixing angles arise from the fact that flavor eigenstates are not aligned perfectly with the mass eigenstates. Instead of that, they are linear combinations of them. Therefore, three angles are needed to describe the rotations required to transform from one basis to another basis. The CP violating phase is an additional parameter that is introduced in the mixing matrix. This phase is responsible for CP violation, which is the difference in behavior between particle and antiparticle under the combined operation of charge conjugation and parity. Including this phase allows for the possibility of observing CP violation in neutrino oscillations. Now, when we will talk about three flavor neutrino oscillation scenario, then what we will talk about the difference in the mass delta m square, delta, these are the three mass eigenstates which we are showing, and here red, green and blue, they are saying a different combinations of nu e, nu mu and nu tau. One is we are calling it as normal hierarchy, and another is we are calling it as inverted hierarchy. If we are having something like this, 1 2 3 m1 m2 and m3, then this is the normal hierarchy, and the inverted hierarchy is this is what we call it as inverted hierarchy. Therefore, as we have not yet seen the absolute masses of neutrinos, therefore when we talk about neutrino oscillation, we are talking about the difference in the mass square of the state 1 and the state 2, or the neutrino mass eigenstate 2 and neutrino mass eigenstate 3. Therefore, what we are talking about, that the flavor states nu e, mu and nu tau are related to neutrino mass eigenstates nu 1, nu 2, nu 3 by a unitary matrix. That means u dagger u is 1, and this parameters of this unitary matrix is there we are talking about the four parameters. Delta m, the thing which we have discussed just before this, delta m square will come in the difference in the masses that we will talk here about, and here we have the different angles that will be theta 2 3, theta 1 2 and theta 1 3. And experimentally these mixing angles are determined. Experimentally we put limits on delta m square. Now, the different experiments that we shall discuss in this class the sensitivity of particularly the different experiments. There we will call it as measuring neutrinos from solar sun, or measuring neutrinos from reactor, measuring neutrinos from accelerators, long baseline and short baseline. These will be sensitive to different parameters of neutrino oscillation matrix, and that we shall discuss. This is the present limit, that theta 13 presently is around 8.4 degree, theta 23 is around 41 degree in normal hierarchy, and theta 12 is 34.5 degree, while delta m12 square, which is determined by in the solar experiment, for example, this is 7.56 into 10 power minus 5 eV square. Delta m13 square, the absolute value has been determined for this, and since we are talking about the absolute value, that means plus and minus sign is yet to be decided, and that is why we are saying that either it could be a normal hierarchy or inverted hierarchy, and from atmospheric neutrino experiments or accelerator experiments we can determine this value, and this presently this value is around 2.55 into 10 power minus 3 eV square in the normal hierarchy case, but it varies when we talk about the inverted hierarchy. Therefore, the important thing is the oscillation probability, and that oscillation probability, as we will see, that will depend upon the delta m square. What is the value of delta m square? How much is the oscillation length? And then what is the neutrino energy? We will see that how, and then we will have the mixing, and this angle theta, and this mixing angle theta will tell us the mixing of one flavor with another. Now, what basically we are talking about? We are talking about, for example, in two flavor scenario, we have a proton beam. It is striking some target, say graphite target, and then from here pions and kaons are getting produced. These pions and kaons, they are giving rise to muon and muon type neutrinos, either mu plus and nu mu, or mu minus and nu mu bar, because you have to conserve the lepton number. And then when a nu mu is traveling in space, it's traveling as an admixture of nu1 and nu2 mass eigenstates, some portion of nu1 and some portion of nu2, that we are representing it by alpha nu1 plus beta nu2. This nu1 and nu2 are the neutrino mass eigenstates. And then when we are putting a detector to detect electron type neutrinos, then what we are finding out that there are few electron type neutrinos as we are observing electrons in the final state. Therefore, starting from a nu mu beam, if we are observing nu e event, then we will say that this is an appearance experiment, because nu mu was there, nu e was not there, but we are observing electrons. Then that means some of the nu mu's have got converted into nu e's, and this is nothing but neutrino oscillation. Or if we are saying that we are producing 1000 nu mu's, and if we are observing 990 nu mu's only, then means the 10 nu mu's have got disappeared. We will say that this is a disappearance experiment. Therefore, we have an appearance experiment in the accelerators, a disappearance experiment in the accelerator, and then the probability of oscillation will depend upon the distance the neutrinos will travel. As I have told you in the last class, that the T2K experiment has the beam from Tokai is being taken to Kamiokande. The distance is around 300 kilometers. While you have beam at Fermilab, and if it is being taken to South Dakota in United States, or you have a beam at CERN and that is taken to Gran Sasso in Italy, the distances will be quite different. And depending upon these distances, the oscillation probability will change. Therefore, these experiments which are scattered around the world, there are many neutrino experiments which are being performed. That the list we have seen yesterday, and we see that the length that those neutrinos travel, they are different. And if we are placing these distances to be 300, 700 kilometers or more than that, we say that we are talking about long baseline neutrino experiments. And for example, this neutrinos from sun, that is again this traveling a very long distance. So therefore, but we can have at the same time short baseline neutrino experiments where relatively you are placing the detector near to this production site. Therefore, for example, if we are performing reactor experiments or accelerator experiments and putting detector nearby distance, then we will call it as short baseline experiments. And if we are putting it at longer distance, then we call it as long baseline experiments. But at the same time, there is another terminology that is being used in the neutrino experiments, that is by the name near detector and far detector. Now, this near detector and far detector is entirely a different concept. This near detector at the production site here, where new mu's are getting produced, these are there to see how many new mu's are getting produced and what is its energy. That is another important point, that we are looking at muon because we cannot see neutrinos. We are looking at muon, we are measuring the muon energy, we are measuring at what angle these muons are coming. From there we determine energy of the neutrinos, how many events we are seeing. From there we will determine the flux of neutrinos. Therefore, energy of the neutrino and the flux of neutrinos, that we are measuring at the detector site. And then these neutrinos are traveling, and say it has traveled to a distance of 700 kilometers, and then we have placed a detector here. Then again we will measure the muon type muons in the final state or electrons in the final state, and then we will see that at what angle electrons and or muons are coming. From there we will determine the energy of these neutrinos. As well, we will also see how many events we are seeing. That from there we will talk about how many neutrinos are arriving. This difference will tell us how many of them have got oscillated. Therefore, you have short baseline experiment and long baseline experiment. This is for the length of the neutrinos those travel, but at the same time you have another terminology, that is near detector and far detector. Near detector is placed to count the neutrinos which have been produced by the accelerator. And then you have the oscillation experiment to see how many of them have got oscillated from one flavor to another flavor. This kind of thing is there in the case of accelerator experiments. This you cannot have in the case of solar neutrinos or in the case of supernova neutrinos, etc. But this is a facility for the accelerator experiments. But at the same time, then you can have the neutrino can travel a distance of say 10 kilometers, 12 kilometers, 20 kilometers, and neutrinos can travel a distance of 1000 kilometers. One will be the short baseline experiment and another will be the long baseline experiment. And then in the next class, we will talk about the two flavor neutrino oscillation and how oscillation probability is obtained in the case of two flavor neutrino oscillation, and then we will generalize it to three flavor neutrino oscillation. Let's stop here. See you in the next class. Thank you very much.